Hello, welcome back to Statistics and Mathematics YouTube channel. Today we are going to continue our series of videos on probability theorem, and today we are going to tackle characteristics with functions. And in our previous video, we tackled what is termed as the moment generating with functions, and that is the same applications that we are going to apply on the characteristics function for us to better our understanding on probability with functions, right? So for moment generating function, we just learned that for moment generating function, we are just going to generate moment for what? The distributions. But moment generating function have some weakness, some limitness, right? So the characteristics function here is going to solve the problems of what the moment generating functions, right? So what is the problem for the moment generating function? The problem for moment generating function is that not all the distributions that we have what moment generating what functions. So the characteristics function here is also going to generate functions for all the distribution that what we have. So the idea of this introduction help us really understand what the characteristics what function. So we being understanding characteristics what function, how can we also define the characteristics function what mathematically? And that is the same thing that we did under the moment generating function. So please, if you haven't watched the video on the moment generating function, for you to better your understanding on the characteristics function, it will be of your good benefit to go and watch the moment generating function before you come to the characteristics function, in order to really understand the concept well and understand it well better. So you see, under the moment generating function, we had the we learned how to generate moment for the discrete and the continuous case. When it comes to the characteristics function too, we are also going to learn how to generate characteristics function for both discrete and the continuous case. So the only difference that we are going to have on this mathematical definition here is what the introduction of what the I, right? So when you go to the moment generating function for the discrete case, we had e raised to the power tx times f of x, summing from 0 to what? Infinity. But here we have introduced I here, e raised to the power it of what? X times what? F of x, right? That is for when our x is what? Discrete. But if our x is continuous to here, the only thing we have added is what? The I, right? The I here. So e raised to the power I times t times x times f of x dx, right? If our x is what? Continuous, right? And then you have to also pay attention to this one. If our I is square is equal to what? -1. Right, so we understand the mathematical definition. Let's dive into the video and solve some examples. So given that f of x is equal to 3 times e raised to the power -3x, where our x is greater than 0 and 0 otherwise, find the characteristics what? Function of what? X. So this is basically a continuous random variable. Our x is a continuous random variable, since we are having our x greater than what? Greater than or equal to what? 0, right? So we are going to calculate for what? The characteristics what? Function, of which this one too is very simple. It's the same thing we did under moment generating function. So what we are going to do is that for the continuous case, we just learned that we are going to move from negative infinity to positive infinity of e raised to the power e raised to the power I times x, times t times x times f of x, right? And then from this question, we just learned that our 0 is what? Greater than 0. So this one will be equal to integral moving from 0 to what? Infinity of e raised to the power I times t times what? X times 3 e raised to the power -3 what? X, right? So this is what we have, right? So if you do it properly, you are going to get integral moving from 0 to what? Infinity. 3e raised to the power -3x plus I t of x. So we are going to factorize -x out of the exponent. So you are going to get integral moving from 0 to what? Infinity. 3e of -x of it minus what? Negative it plus what? 3. So this is what we are going to have. And once we get this, we can what? Do what? Integrate. Okay, so I have the solution here. Let's go into the solution sheet to get it very right. Okay, so once we have this one, this is what we are going to get, and then we did it up to what? This point. Okay, so here we are just going to integrate what? This function. We are surely going to integrate this function, right, with respect to x. And once you integrate this function very well, we are going to get 3 divided by 3 minus it, right? Yes, where our t is less than, sorry, where our t is not less than 3. Yes, our t is what? Less than what? 3. So that is what? That example for you. So here it can be seen that if our moment generating function x exists, then our characteristics function is equal to what? The moment generating function if we substitute in our it, right? So if we have a certain function, if you have a certain function and then we have been asked to maybe calculate for the moment generating function, and that moment generating function for that particular random variable exists, right? If we are asked to calculate for the characteristics function, all that we are trying to tell you is to just replace to just replace it to what? The moment generating function. So let me write it for you to better understand it. So here, let's say the moment generating function, indeed the moment generating function for this particular example, right, will be giving us 3 divided by 3 minus what? T, right, as we have here. So if you have been asked, let's say you have this moment generating function and then we have been asked to calculate for the characteristics function, the theorem is just telling you that there is no need for you to calculate the characteristics function. All that you have to do is to just substitute it to wherever you see t, right? So you are going to get 3 over 3 minus it, right? So that one will give us our characteristics function. So that is what the theorem is trying to help us to understand. So let's go to our second example. So the second example, as I said, says given the discrete random variable y as below, find the characteristics function of what? Y. You see this question already, we solved it under the moment generating function, right? And then we said that under the moment generating function, we had our moment to be 0.6 e raised to the power t plus 0.4 all raised to the power 12. That is what we had under moment generating function. So basically what the theorem is also trying to tell us is that once the moment generating function exists, right, wherever you see t, we are just replacing that place by what? I of what? T. So here we are going to get 0.6 e raised to the power I of t plus 0.4 all raised to the power 12, right? So that is what we are going to have. But let's follow the procedure to get the characteristics function. Let's follow the normal procedure to get the characteristics function for you to really better your understanding. So let's dive into the solution to get it. Okay, so this one we are also going to sum from 0 to 12 of e raised to the power ity times the function, and the function that we have here will be 12 combination y times 0.6 raised to the power y times 0.4 raised to the power 12 minus y. And then you see we are having y here, we are having y here, right? So they are going to multiply and then just factorize the y out. So we are going to get summation moving from 0 to 12, 12 combination y times 0.6 e raised to the power it all raised to the power y times 0.4 raised to the power 12 minus y. And then in the moment generating function video, I told you that this represents what? The binomial expansion formula, of which we have that to represent a plus what? B all raised to the power at n. So when we come here, this one represents our a, this one represents what? Our b, and then the 12, as you can see here, represents what? Our n. So we just substitute it in here to get what we have here. So you see that is the same thing. So since this exists, the moment generating, since the moment generating function exists, we can just replace that place by what? I times what? T, to get your answer. So let's dive into understanding some of the theorem to under the characteristics what function. In fact, it's something similar to what we treated in moment generating what? Function. So we are saying that the characteristics function of the random variable x, right? If you have that characteristic function and then you have not applied any differentiation to that characteristic function and put t is equal to 0, you are surely going to get what? 1. So that is the same theorem under the moment generating function too. When we put t is equal to 0 to any moment generating function without applying any differentiation to it, you are surely going to get your answer to be 1. And the theorem here also says that if y is equal to a plus bx, where a and b are constant, then the characteristics function of the random variable y will be equal to e raised to the power I t a times the characteristic function of x, right? Of which this is what we are going to get, right? And then if you want to prove it too, that's the same proof I walk you through when we are treating the moment generating function. The only thing we are going to do here is to just add the I to it. So if you haven't watched the moment generating function, you kindly watch it for your understanding, okay? Yes. And then this theorem is also telling us that if nth moment of x exists, let's say if you are having nth observations, right, of a random variable, and then that moment generating function for that random variable really exists, then we are saying that the nth derivative of the characteristic function of the nth derivative of the characteristic function also exists, right? And then if you take the nth derivative of the characteristic function and put t is equal to 0, we are going to get I raised to the power k times the expectation of x raised to the power k. The reason why we are having I raised to the power k is because we are dealing with characteristics function. And in the earlier section of this video, I told you that I square, right, is equal to -1. So you have to put note to that, right? So as we go to I cube, we are going to also get what? If you have I cube like this, we are going to also get what? -1. If we have I raised to the power 4, we are going to get 1, right? So as I continue to increase, we are going to get alternative numbers between 1 and then -1, okay? Yes, so that is what I want you to really understand. So you see, it's the same thing that we explained earlier under the moment generating function. So let's solve an example to better our understanding here, okay? Yes, so there's an example, okay? He said a discrete random variable has characteristics function that which is equal to e raised to the power 3 bracket open e raised to the power it minus 1. Find the expectation and variance of x, right? And then we just learned that if you want to find the expectation of x, you first take the derivative of the characteristics first, the first derivative of the characteristics function, and put t is equal to 0. So when we take the first derivative of the characteristics function, we are going to get 3i times e raised to the power times e raised to the power it bracket open e raised to the power 3 bracket open e raised to the power it minus 1, and just put t is equal to 0. The whole of this place will turn to 0, of which e raised to the power 0 will give us 1, and then e raised to the power 0 here will also give us 1, right? So we are going to get 3 times I, of which our final answer will be 3. And then you see, this is the moment generating function for Poisson distribution. And you see, for Poisson distribution, the mean and variance is equal to they are the same. So the variance here too is also the same thing, okay? That property only holds for Poisson distribution. So if you get other distribution, they are not like that. You have to take the second derivative, and then the variance will be what? We take the second derivative, the variance will be what? Expectation of x squared minus expectation of x all squared. Okay, this is how we are going to calculate for the variance for the other distributions. Okay, yes, so that is that. So let's continue our video. Okay, so we have what is termed as what? The uniqueness theorem, right? So for the uniqueness theorem, we also discussed uniqueness theorem when we were treating the moment generating function. So here we are saying that corresponding to each characteristics function phi, there is a unique distribution function having phi as what? A characteristics function. So we mean that every distribution have its own unique characteristics function. That is termed as what? The uniqueness theorem. And then under the uniqueness theorem too, we are having independency also exists under uniqueness theorem, and let's see how the independency too is explained under the uniqueness theorem of the characteristics function. So here, let x1, x2, to xn be independent random variable with a characteristics function phi s sub 1, phi s sub 2, phi s sub 1, n respectively. If y is equal to the summation of the independent random variable, then the characteristics function will be the product of each of the characteristic function of y will be the product of each of the characteristic function of the xi. right? So if you are timesing the xi up to n, it means it will be what the product in the form of product. That's the same thing we did under the moment generating function. So more or less we can write this as what? Phi of x1 of t times phi of s2 of t times phi of s3 of t times what? Phi of xn of what? T. And then this one, the multiplication of the whole of this is equal to what we have here. Okay, yes. So let's solve example under this to also better our understanding. Okay, so when we come here, we have an example here. It's saying that let x1 x2 to xn be a random sample of size n of x if the characteristics function of the random variable x is given as 1 minus 2it all raised to the power negative 1 over 2 times v. Find the characteristics function of a y sub n, which is equal to the summation of what? Xi, moving from 1 to what? N. Okay, so that means that we are going to have our y is equal to x1 plus x2 plus x3 plus plus what? Xn. And then since this is independent random variable, its characteristics function, the characteristics function for y sub n will be the product of what? The characteristics function for the s sub what? N. So here will give us characteristics function of x1 times x2 times x3 times to what? X what? N, right? To what? Xn. So here is no 2, it's what? Xn. Okay, a minute. Here is what? Xn, as we all learned, right? So if you multiply everything, since you are summing up to n, it means that that one will be the characteristics function, right? As we had in the question of characteristic function of the random variable x being this one in the form of this. Since we are just multiply it n times, we are going to get the characteristic function raised to the power n, right? And then you see we are having negative 1 over 2 v as an exponent. So this exponent will times multiply this exponent. We are going to get our final answer to be this one. Okay, yes. And then also the second question is telling us that if our wn is equal to y sub n minus n divided by square root of 2n, right? We should find the moment generating function for wn, right? And then just now we just treated something that I'm coming. If we have, let's say, y which is equal to a plus b of x, this one is equal to e raised to the power ait times the moment generating function of x of bit. Okay, this is what we had. So that is the same thing, right? So let's just break it down for us to get something similar like this to understand what I have calculated there. So here we are going to have y sub n minus n all divided by square root of 2n. So it means that y sub n divided by, we can also write it in the form of y sub n divided by square root of 2n minus n divided by square root of what? 2n. We can write it in this form. And then this is the same thing in this form. Just like for this part, our constant a here is what? Positive. But when we come here, our constant of n divided by square root of 2n here is what? Negative. So that's the only thing that's going to change, right? So here we are just going to take this formula. Our a here will represent negative square root of n divided by what? 2, right? So when we come here, we are going to replace where we see a by negative square root of n divided by 2. So you are going to get negative it times square root of n divided by what? 2 for the first part, right? And then we just take the characteristics function that was given, right? And also replace the place we see the b. And then we know that the b represents 1 over square root of 2n, right? So we are going to replace that place by 1 over square root of 2n. So that helps us to get 1 minus 2it divided by square root of 2n. And then all raised to the power negative 1 over nv, right? So that's the solution to this particular question. Okay, so this is Statistics and Mathematics YouTube channel. Please, if you haven't subscribed, kindly subscribe, like and share so that this video will get to your friends for them to also better their understanding on this particular video of the characteristics function. In our next video, we are going to learn something on the inversion formula.